So here for the beginning of Organic 2, we start with two of our most important reactions that we cover over the entire year. And the reason I say that is you may recall in Organic 1 I commented a number of times that while we have a lot of reactions that we're going to learn, well over 100 different reactions, we only have maybe a dozen, maybe a few more mechanisms that cover almost all of the steps that we see in reactions. And that's especially the case here. These two mechanisms, these two reactions, SN1 and SN2, are mechanisms that we are going to see over and over and over again. And so I can't stress how important these are. And so we're going to start these as reactions of alkyl halides, but we want to think and remember that these reactions are not just going to be limited to alkyl halides. Alkyl halides are probably our most common starting material for SN1 and SN2, but we will see them in a lot of other cases as well. So we need to start by recalling two of our most important definitions, being nucleophile and electrophile, because both of these will play an important role in both SN1 and SN2 reactions. In fact, the N in SN1 and SN2 stands for nucleophilic. So, what are these definitions again, if you've forgotten them? A nucleophile is a substance that is nucleus-loving, recall that's literally the derivation of the word nucleophile. Nucleo for nucleus and phile for loving. So a nucleophile is a substance that is nucleus-loving and forms new bonds by donating a pair of electrons. That's essentially the opposite of an electrophile. An electrophile is electron-loving. And it forms new bonds by accepting a pair of electrons. And as we saw in the chapter on alkenes especially, we also saw it in alkynes. But many reactions are the reaction of a nucleophile attacking an electrophile. Again, you may recall that in a reaction like this. You recall that the alkene was the nucleophile because it donated a pair of electrons to the hydrogen, which was the electrophile. Now, we never really defined what this bromine was, other than to say it was going to, sort of get pushed out in this step, and then it ended up playing a role in the next step. But something like this bromine here does have a formal name, and the role that it plays is it's known as a leaving group. And that term is hopefully fairly self-explanatory, because a leaving group is an atom or an ion or a group of atoms that leaves during a mechanistic step. All right, now the reaction we're going to start out by looking at here are these reactions known as nucleophilic substitution. And it is just what it sounds like. It's a substitution reaction, so we're replacing one group with another. And it's triggered by a nucleophile coming in. So if we have an alkyl halide here, for example, we can add a nucleophile to it, such as hydroxide. We know that the carbon-bromine bond is polarized. Bromine is more electronegative than carbon. So that means we have a partial positive on carbon, partial negative on bromine. Well, the hydroxide, with its negative charge, is going to be a nucleophile. While the carbon that has the halogen attached to it is electron poor, and it's going to be an electrophile. So one thing that could happen here is that the hydroxide, our nucleophile, attacks the carbon that's partial positive, which is the electrophile, and then kicks out the bromine, which we would call our leaving group. And so we get our product. And what has happened overall in this reaction? The nucleophile has substituted the leaving group. Hence our name, nucleophilic substitution. Now, some of you might be wondering what happened to the bromine, because I didn't draw that in the product. And sort of the simple answer from an organic chemist's point of view is it's not an organic product, so we don't really care. Now, does that mean our equations that we've drawn is not balanced? Yes, I suppose in theory it does. But the fact is, when we look at organic reactions, a lot of times the inorganic type byproducts, such as Br minus here, it's not necessary to draw them in. And the reason for that is actually fairly complicated. The reason for that is often it's not quite this simple. That Br minus might end up doing other things with things that are present in the reaction solution. And so, or in some cases, we might have a group that is removed from an intermediate, but there's 3 different ways it could be removed. And either we're not sure which one is the way that it's actually removed, or it's just not, or it's not known, or it's just not important, because maybe all of them are taking place. And being organic chemistry, what we're concerned with is here's the organic starting material, and here's the organic product, and that's in many cases all we need. Now, this idea of nucleophilic substitution is actually not a new reaction to us. Where have we seen it before? Well, maybe we recall alkynes. And you recall, if you had a terminal alkyne and you treat it with a strong base, we could deprotonate that alkyne. And then that anion, if we added an alkyl halide to it, the anion from the alkyne, the acetylide, attacked the alkyl halide, kicked out the leaving group, and formed a new carbon-carbon bond. So while we didn't truly get into it at that point, this was in fact an example of a nucleophilic substitution reaction. We had a nucleophile attacking an electrophile, which triggered a substitution reaction. Now, one of the things that complicates these substitution reactions is competition. So we're here talking about nucleophilic substitution, but it turns out there's a competing pathway. And with any alkyl halide, or as we'll learn later on, anything with a leaving group. So the reactions we learn about here, while we're mostly going to talk about them with alkyl halides, this can be anything that's a good leaving group. What's a good leaving group? That's something we'll define later on. So the competition is with a process known as elimination. And what that means is if we have a hydrogen on the carbon next to the leaving group, so this is the carbon with the leaving group, so by next to we could be referring to this carbon or this carbon. If we have a base present, the base can remove that hydrogen. The electrons from the carbon-hydrogen bond shift over to form a new carbon-carbon pi bond and kick out the leaving group. And so the result of an elimination is we get an alkene. Now, given that there are some similarities between a molecule being a base and a molecule being a nucleophile, how do we determine which one can take place? And are there cases where both elimination and substitution can take place? So there's a number of factors we have to look at. What is the degree of substitution? And that's for both the base or nucleophile and the leaving group. So is the leaving group primary, secondary, tertiary? That plays a big role in what's going to happen with the reaction. What is the leaving group? What is the nucleophile or the base? Is it something that functions better as a nucleophile? Is it something that functions better as a base? And finally, what is the solvent? And so these topics are going to make up sort of the first major chunk of this course. The idea of the substitution reaction, the nucleophilic substitution, and the elimination. So overall, what we're going to end up with are 4 reactions: SN1, SN2, E1, and E2. And what those factors that we just discussed on the previous slide are: degree of substitution, the leaving group, the nucleophile or base, and the solvent. By examining all four of these properties, we can determine which of these four reactions is going to take place. So we'll pick up in our next video by digging into the first one of these reactions, which is the SN2.